give a talk about extending Pythagoras.
So thank you. This is joint work with Professor Gowdy back when you could actually go to someone's office and be close enough to write on the same piece of paper. I had to choose a topic that I thought would have less than 100 people coming. It's still a fun topic, but all right. So does everybody here know the Pythagorean Theorem? Excellent. All right. So I normally would wear my Ohio State shirt when I'm giving this talk and mention that it's the Ohio State University. That in mathematics, we don't normally say the proof, we say a proof, because there are different proofs and they highlight different things. As of earlier in the day, I was actually going to have to chair a school committee meeting, and so I had to dress somewhat nicely. By this point in time, my day has now changed, and I can now actually afford to lecture for quite a long time today about stuff like this. So what I want to do is I want to talk to you a little bit about how you might sniff out some theorems, how you might sniff out some relationships, either with data or with just a little pure thinking. And I will choose the Pythagorean Theorem as the motivation because I'm assuming everybody has either seen the Pythagorean Theorem before or can fake, nodding, oh yeah, they're well familiar with that. All right, so the Pythagorean Theorem, just for definiteness, if you have a right triangle A, B, and C, a squared plus b squared equals c squared, sometimes they draw the hypotenuse the other way, and sometimes they flip the A and the B. I do not think there's really a canonical choice of which way you do it. How many of you can give a proof of this right now? How many can give two proofs? All right, so since we've already whittled down to, I will not ask them how many can do three proofs, but there's lots of different ways of proving this, and different proofs will highlight different aspects of the problem. So here is one proof going all the way back to Euclid. I think it's from book 1, proposition 47, because it says book 1, proposition 47 from the webpage I stole this from. If you put it in color, and it's still the same proof, this really doesn't speak to me at all. I'm sure you could go through and do the calculation. When I look at this, I don't really see, it doesn't really speak to me about what's going on with Pythagoras. This one really doesn't speak to me at all.
I did say something important. I don't know how rigid, but if you go back, I think buried in there is the assumption that there's a line parallel to every other line. You have to use the fifth axiom of that. And that's why he waited the last minute to prove it. And that proof is much longer. It's just than all the other earlier.
And I would not be surprised on that based on what's going to come later in the talk. So this one is another way where you're chopping things up and matching things. And at the end of the day, it should get everything works. This is the first proof that I remember seeing that I can reproduce. I learned this in a physics class. So imagine you have 4 right triangles. I'm going to assume that we know how to find the area of a rectangle. It's just length times width. If you have a right triangle, it's half the area, so it would be 1/2 x times y. If you are not comfortable with that, the doors are open, so you can flee immediately. We have to assume something, or we're going to get nowhere interesting. So we have 4 right triangles. So the area of those is going to be 4 times 1/2 AB. And then you have a square with a little bit of calculation. Each of those angles is 90 degrees, so you get c squared. But you also have a larger square of side length a plus b. So a plus b squared is going to be c squared plus 4 times 1/2. So when the algebra settles, you get a squared plus b squared equals c squared. There's other ways of writing it. Here is a slightly different version of the same proof. Probably our most famous graduate, not because he became president of the United States of America, but because he is credited with a proof of the Pythagorean Theorem. I am employed here, so I will not talk at all about looking at just half of the picture on the left and what he's doing, but he is given official credit as a proof of the Pythagorean Theorem for this trapezoidal argument. Okay, so the question is, how do you find these combinations? Especially if you go back to something like this, where are these lines coming from? A lot of good geometry proofs always come down to how do you choose to draw the auxiliary lines? So what I want to do is I want to talk a little bit about dimensional analysis. So I was a double major, I did math and physics, though I really hammered in dimensional analysis in physics, got a little bit of it in chemistry classes in high school. I'm curious, how many people have seen a lot on dimensional analysis? Not too many. All right, so here are 5 candidates for the Pythagorean Theorem. In some sense, we know this is a bad list, right? Can anybody give me any reason for or against anything on this list? Yes?
It would not make sense for it to be the first one because if A, B, and C all have the same units,
good.
then A will have and the right hand
Good.
side went to the 17th.
Good, so this will be meters to the 17th is meters squared. So 1 is right up. What about the second one? Yeah, the lack of symmetry in A and B makes me a little bit worried about the second one. What about the third? It's also, so 1 is, you could just say same, but I think it's even a stronger reason why the third one is bad. Yeah, it could be negative. And you should not have c squared being a negative number, unless you're doing special relativity. What about the fourth one? Is this passing some of the smell tests? It's symmetric. It has the right units. All right, what about the fifth one? It's also symmetric. 17 is a wonderful number. Just ask Gauss. Is the last one fair game? Oops, I touched the screen. Anybody know any relations between the sides of a triangle? Yes.
A plus B has to be larger than C.
A plus B has to be larger than C.
And A plus B squared.
Right, so A squared plus 2AB plus B squared would be A plus B squared. So this is more than just A plus B squared. So you have C squared is more than A plus B squared. So the last one is actually out as well. So the middle one, I'm sorry, the second to last one at least passes our tests. It's not right, but at least passes our test. It's a candidate. So here's a dimensional analysis proof. So area I claim is a function of the hypotenuse C and the angle X. Because if I fix the angle and the hypotenuse, then the sides A and B are uniquely determined. And then I can construct the area by just multiplying A and B. Technically A is going to be C times sine of X, B is going to be C times cosine of X. But I don't really care about trig functions right now. Area is going to be a function of the hypotenuse and the angle. I claim not only is it a function, but it's got to be a very specific form. It's got to be some function of the angle times the hypotenuse squared. And this is from unit analysis. If I triple C, I'm going to triple B and I'm going to triple A. I'm assuming we're all comfortable with corresponding parts of congruent triangles are congruent CP, CTC. Yes? Sound vaguely familiar? So if I triple C, I triple B, I triple A, so the area is going to go up by a factor of 9. So the area has to be proportional to the hypotenuse squared. So all geometry proofs come down to drawing an auxiliary line. So you have to add a line to this. Anybody have any thought about where we could draw a good line? Yes?
Drop an altitude from the right angle?
Yeah. I'm not sure if it's still called dropping because we're going up with the way it's going. So climb along.
Drop it like
Drop it from the hypotenuse to draw this line. And so with the creative names of triangle 1 and triangle 2, you see that all the triangles are actually similar. So this is angle X, this is 90, this is 90 minus X, so this has to be X as well. So now we have 3 triangles that all have an angle X. What's the area of this triangle up here? F of X times A squared. And the one over here is going to be F of X times B squared. And the whole one is F of X times C squared. So now what do? We cancel the F of X. But because this is a math talk, we have to justify this. We have to show that F of X is not 0. Well, if F of X is 0, I hear some laughing, which is good. Yeah, it can't be. Or more rigorously, if F of X is 0, then the area is 0, and we know the area is not 0. So we can cancel, and we get A squared plus B squared is C squared. So this is a dimensional analysis proof that gives you Pythagoras. It gives you a little bit of a sense of where it's coming from. Here's another dimensional analysis. Has anybody seen the pendulum problem from a physics class? So the period is proportional to a couple of quantities. So what do we have in play? We have the length of the rod in meters. We have the acceleration due to gravity in meters per second squared. We have the mass in kilograms. We have the period it takes the bob to go back and forth, which will be in seconds. And we have the angle, which is in radians, which is essentially unitless. And so if I want to get period, which is in seconds, I have to combine all of these quantities in such a way to get seconds. And a little bit of work, so there's only one combination that will work. It's going to be the square root of L over G, and I can have any function of theta, any function of the radian part. And so without even doing any experiments in the lab, you can already predict that if you were to quadruple the length, the period should double. All right, so what I want to do now is I want to shift to trying to guess Pythagoras. So imagine we don't know what the Pythagorean theorem is. We didn't see any of these proofs, even though there's well over 100 different ways. Can we try to figure out what it is? Almost surely none of you will ever be in a situation where you have to guess the Pythagorean theorem. But what you might be in a situation is where you have some data and you're trying to sniff out a relationship. And so the reason I wanted to talk about this today is the real point is how do you sniff out relationships? So we want to guess the functional form. We've got a couple of parameters. And let's try some special cases. Let's try some simple things. The simplest thing is maybe a linear relationship. And if the linear relationship doesn't work, then we can try a quadratic relationship. If that doesn't work, we can try a cubic. If that doesn't work, then we apply to the NSF for funding and say that, this is an open problem, All right, so let's guess that C is equal to alpha A plus beta B, where alpha and beta are unknown. Can anybody give me any information about alpha and beta? Positive. What else? They should be the same because we should be able to switch the roles of A and B. Anything else? Strictly less than 1, or could they exactly equal 1?
I guess. I don't know. I mean,
because you can have the degenerate triangle where the hypotenuse, again, it's not going to be a right triangle, it'll be a 180-degree triangle. But maybe it's at most 1. Can anybody think of any triangles where you might be able to sniff out the values of alpha or beta, any extreme cases? So one is isosceles right triangle. Okay. The other one is a very long triangle with very small height. Because as it gets longer and longer and longer, these two sides are approximately the same. So as you take bigger and bigger and bigger lengths and have that height shrinking down to 0, you see that the only possibility is alpha equals beta equals 1. And so the relationship has to be C equals A plus B. Does this make sense? Well, now we've already said this. We now use the isosceles right triangle, which 2 people were kind enough to mention. That's the simplest value. Take A equals 1, B equals 1. And so if we put them together, we get a square. And if we assume that the hypotenuse of the right triangle is just the sum of the two sides, then the hypotenuse has to be 2. So we have a square that's 2 by 2. And now we can calculate the area 2 different ways. The area of a 2 by 2 square is 4. But each of these triangles is 1/2 base times height. So you have 4 times 1/2 is 2. So we get 4 equals 2. So we now know that the Pythagorean relation cannot be linear. So there's no linear thing that works. So let's try quadratic. Any information you can give me on alpha, beta, and gamma? Same. Alpha has to be equal to beta. They should be between 0 and 1. They should be positive, should not be larger than 1. What about gamma? The 17 trig. It probably can't be maybe more than 2 in absolute value. You might be able to do some information like that. So the question is, as before, if we look at those long, thin triangles, we get alpha equals beta equals 1. The hard part is the gamma in the middle. And so if we again take our isosceles right triangle, now we have the hypotenuse is C. And so if we do the calculation, we'll get, if we equate areas, we get C is equal to the square root of 2. But C squared is supposed to be A squared plus gamma AV plus B squared. So we get 2 is equal to, I think, gamma plus 2, so gamma equals 0. And so we get C squared is A squared plus B squared. This is not a proof of the Pythagorean theorem, but it does suggest that it might be A squared plus B squared is C squared. And now we have an idea of what to try to prove. If you ever try to prove things by induction, it's typically a lot easier when you know what you're trying to prove by induction. How many people have not seen this example? Okay.
Have not seen?
Yes, 16 over 64 in lowest terms. Yes? It's 1/4. 19 over 95 in lowest terms. 49 over 98. 1/2, 12 over 24, 1/4, right? Because 16 over 64, you cancel the 6s and you get 1/4. The 19 over 95, you cancel the 9s and you get 1/5. 49 over 98, you cancel the 9s and you get 4/8, which does reduce to 1/2. So clearly 12 over 24 must be 1/4. So just because we've shown it works in a case, this is not a proof. Someday, if you're on the other side of the table and are grading exams and papers, you will see stuff like this. What we should really do is we should try to find, are there other right triangles where we could test the c squared equals a squared plus b squared? So what might be another one we might be able to do? Anybody think of any other triangle that has at least a chance that we might be able to do something with it? Yeah, 30, 60, 90 is the only other one that comes naturally because it's coming from an isosceles, I'm sorry, an equilateral triangle. So if we do the 30, 60, 90 triangle, maybe there's a hope of getting something for that. Right. So I am embarrassed that I had never thought of this until I was having a discussion with Professor Garrity. But the question is, how would you extend the Pythagorean theorem to other settings? So out of curiosity, how many of you have ever thought of what would Pythagoras look like in a different space? So given that you're all younger than me, you've now at least done this before I did. Almost all, sorry. So what would it look like on the sphere? So anybody have any thoughts as to what the Pythagorean theorem would look like on a sphere?
I mean, as everything gets really small, the sphere looks like just like flat.
Okay, so if the triangle gets very small, it's going to look flat. And so what should it reduce to? It should reduce to the normal Pythagorean theorem. So whatever theorem I get for Pythagoras on a sphere, in the limit as the radius of the sphere goes to infinity, and I keep the size of my sides fixed, it should reduce to what we see already. So the reason I wanted to give this lecture is because this is a chance to do a little stuff that I'm doing in multivariable calculus. The problem is, I mentioned earlier that I was a double geek. I did math and physics as an undergraduate. The two departments have different notation for spherical coordinates. And the way I always learned spherical coordinates was, it's theta that comes down from the z-axis, and then phi, no, I know, and I agree that mathematically this is terrible notation because you want to reduce to polar coordinates. Polar coordinates is little r theta, so you have rho as the length in spherical, and then you have phi coming down, and then you can do theta as before. So when Professor Goldmacher was kind enough to extend me the invitation with less than 24 hours notice to give the talk today, I did a very quick search and replace to switch all the thetas to phis and phis to thetas. I think I got everything. The safest way to do this is you shift all the thetas to, say, gazubel. Then you switch all the phis to theta, then you switch gazubel to. So hopefully everything was fixed. All right, so I'm going to use the math notation. So phi is my angle coming down from the z-axis. Yes? Did I miss one already? Oh, okay. Oh, okay. That's just not the hand gesture I'm used to you doing. So phi is coming down from the z-axis. So z is going to be rho cosine phi. And now it's like I have a circle above the xy plane, and the radius of that is going to be rho sine phi. So I now have a circle of radius little r, which is rho sine phi. And then I'll have my polar coordinates. So I'll have cosine theta for x and sine theta for y. Okay, so what would the Pythagorean formula be on a sphere? Well, as was mentioned, if a, b, and c are small relative to the radius r, it should look like plane of Pythagoras. Things can be a bit more interesting. We can actually have an equilateral right triangle on the sphere. So go from the North Pole down to the equator like that. So a good thing to look at is maybe it only depends on the ratios a over r, b over r, and c over r. And maybe I can try to sniff out a formula like that. And then after a little bit of playing, maybe cosines might play a role. And one of the reasons is we know that on a circle, the reason we use radians is if you have a circle of radius 1, the angular measurement in radians is equal to the arc that it covers. And so this is a great way to pass to lengths. So using a little bit of calculus, the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial, et cetera, et cetera, et cetera. If u is very, very, very small, cosine of u is approximately 1. To do a little bit better, it's 1 minus u squared over 2. And so what I'm going to do is I'm going to just compute the cosine of a over r, b over r, and c over r. So I get 1 minus 1/2 a squared over r squared, and similarly for the other two. And just playing around with them a little bit, if we multiply the cosine of a over r and the cosine of b over r and expand, well, since a over r is small, then if a squared over r squared is small, b squared over r squared is small, and their product is damn small. It's a technical term. We can ignore damn small things and just throw them away. And so the main part of this is going to just be 1 minus a squared plus b squared over 2r squared. And so on the other side, we get 1 minus 1/2 c squared over 2r squared. So we then multiply through by 2r squared, we get, the ones cancel nicely. We get c squared is about a squared plus b squared minus 2a squared b squared over r squared. Is this a proof? Not in our department, right? But it at least suggests that this might be a good thing to try. And so, I'm going to go through this very quickly. We have the dot product. If I have two vectors v and w, v dot w is just v1 w1 plus dot 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 vn wn. And one of the reasons we love the dot product so much is if I have the dot product, it's equal to the magnitude of v times the magnitude of w times the cosine of the angle between them. So there's a nice way to get angles. And we know that there's a relation between angles and length. If you're on a circle, if the circle is radius 1, then the angular measurement is the same as the arc length. If the circle is radius 5, you just multiply by 5. So we have the law of cosines. If you haven't proven this, it's a fun thing to try to prove. You can go through and calculate everything, calculate all the different lengths. I'm not going to go through all the algebra, but with a little bit of work, you can get the law of cosines, which relates this angle here and the length over there. And then I'm just going to choose 3 points, P0, PA, and PB. Without loss of generality, you can always choose one point to be the North Pole. And then I have 2 other points coming down, and then I need to just find the angular length. I don't want to go through all the algebra. I just want you to see that if you wanted to do the algebra, you could do the calculation. You could find out what is the angular length. The theta is not going to matter. All the theta does is it just turns me around. It's the phi coming down from the z-axis that matters. So the first one from the PA to the North Pole would just be phi a over 2 pi. So I'm going to call that my a over r. And similarly for the second one. And then I have to figure out, of course, the length of the third side. And so the key thing that I'll be using in all this is the dot product formula. P dot q is length p, length q times the cosine. All right, so the other thing is you can always play a few games, just make your notation a little bit easier. I might as well choose one of the points to correspond to theta equals 0, because I can just spin the whole sphere. And I know I'm supposed to have a right angle, so then I know the other theta has to be pi halves. And so now it's just a question of, oh good, I have a lot of zeros, so when I'm doing the dot product, zeros hitting something that's not 0, it's still 0. I've got 2 zeros, so most things are going to cancel. And so just when you do all the calculations at the end of the day, you get the cosine of the angle is cosine of phi a, cosine phi b. And here is now a proof of spherical Pythagoras. So I have maybe 3 minutes left before lockdown. What should we look at now that we've done spherical Pythagoras? Yes, and there's a reason why Professor Adams is not here, because I cannot risk having a ringer in the class for this. What do you think the formula might be in hyperbolic space? And for those of you who have not seen hyperbolic space, I am deliberately not saying what that is. Any guesses? Does anybody know any functions involving hyperbolic? Yes?
Hyperbolic sine and hyperbolic.
Yeah, this thing's called hyperbolic sine and hyperbolic cosine. So one way of writing cosine of theta is e to the I theta minus e to the minus I theta over 2. Hyperbolic cosine is just e to the theta plus e to the minus theta over 2. Or it's cosine of an imaginary angle. Any Foxtrot fans here? One of my favorite Foxtrot comic strips is they are at a science camp, and one of the kids is upset about these lousy camp-issued calculators. It's not calculating the cosines correctly. It's giving me 1.7, and everybody knows the cosine can't be 1.7. And then Jason goes, you've got it in hyperbolic mode. And then Marcus goes, if you want, you can have my calculator. Some of us don't need them. What might you guess the answer is for for hyperbolic Pythagoras? Put in an H, right? Right, and then the H, well, but actually, if we multiply by H, we're in trouble because we need an H squared on one side.
Oh.
So as was remarked, cosine of X is 1/2 e to the IX plus e to the minus IX. Hyperbolic cosine is just e to the X plus e to the minus X. It's the same as cosine of the imaginary angle. We have a lot of fun identities. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. Hyperbolic sine of X plus Y, we still have a double angle we still have an angle addition formula in the two cases. And so I will leave the proof as to whether or not this is correct as an exercise. It's the natural thing to try. All right, so conclusion, even if you've seen something for years, there's almost surely another question you can ask on it. And if you can train yourself to ask good questions, it will lead to new discoveries sometimes. A lot of times, maybe the question's already been asked, or maybe there's a good reason no one has asked it. But sometimes it will be something that nobody has thought to ask. And just, you have blinders on and everybody's always used to using this for a specific purpose. That they have, well, what else could I do with this? Especially if you are coming at a subject from a different perspective, from a different discipline. So one of my favorite quotes is, if all you have is a hammer, pretty soon every problem looks like a nail. There's a lot of ways to look at this. One way to look at this is whatever you have, if you're good at something, you will convert it to being able to use the hammer. If you ever listen to any presidential debate, it does not matter who the candidate is, whatever question they asked, after about 10 to 20 seconds, they segue into whatever they wanted to talk about. If you have something that you're really good at, you try to convert to that. But there's another way to look at this. Go to the land of the screwdriver. If they could have solved it using a screwdriver, they would have. They're smart people. Their tools are not working. If you have a different tool set, you have a real opportunity to make progress. If you read some of Feynman's stories, he talks about how he got a reputation for brilliance in integrating. And what happened is, whenever people came to him with an integral that they couldn't do, he assumed they had already tried all the standard stuff, because they're smart people. This is Princeton, this is MIT. If the standard stuff would have worked, they wouldn't come to him. He knew about differentiating under the integral sign to prove relations, which most people don't. So the very first thing he would try would be differentiating under the integral sign, which would often work. And he would get this wonderful reputation of being able to solve difficult integrals. So I really encourage you, and this is one of the nice things about being at a liberal arts college, is you get a lot of different skill sets. You have the ability to talk to people in different subjects. I've worked on projects in accounting, marketing, economics, computer science, geophysics, statistics, physics, lots of different areas, because I can convert a lot of these problems to mathematics, and I have a different tool set than other people have. So looking forward to seeing what conjectures you guys get in the future. Thank you.